Welcome back to this third week about functional programming in OCaml. This week will be devoted to algebraic data types, which are very important kinds of types that you can use in OCaml. To understand them, we will present them progressively by first showing how you can tag values, how you can define recursive types, and using these two features, what kind of tree-like data structures you can define. Based on that, we will define a story generator. Just after that, I will show you how you can make an algebraic data types polymorphic, and we will conclude with advanced topics. So let us come back to our database example, and more precisely on the type that we have assigned to the engine function. This type is not really satisfying because if you look at the return type of our engine, it is a triple, but sometimes some component of this triple is meaningless. Indeed, when you have a query which is an insertion, only the database component is meaningful. If you are looking for some contact, only the second component is meaningful. And if the status is false, then the two other components are meaningless. So can we fix that and find the types that could capture this constraint in a better way? What we want to do is to change the type of the engine into something like that. So we have replaced the return type of the function with a new type named query result. And what we want is for a value of query result to be either an error or a new database in case of an insertion or deletion query, or a contact and its index in case of a search query that was successful. And in fact, in OCaml, you can just write a type declaration that really mimics this informal description. You define a type query result using three cases. The first one is error. The second one is a new database followed by the database. And the third one is a found contact case followed by the contact and an integer. So what we have here is called a sum type. It is a disjoint union of types. It's a way to take several types and to join them into one unique type. But then you want to understand from where the different values on this type are coming. And to do that, you use tag. So a tag is an identifier that must start with an uppercase letter. And what you have is the fact that tag identifiers are unique and distinct in an algebraic data type. So a tag characterizes one specific type in this disjoint union of types. So now, how can we construct and observe values of this type? Well, the first thing to know is the fact that tags are also called constructors. So when you want to build a value of a subtype, what you have to do is to construct a value of that type by applying a tag to the argument, the components of your value. So the tag will be a marker that will be used to classify values during the execution of the program. The syntax to mark or to tag a set of values is just the following one. You first write the tag, and then between parentheses, you write the different components that must be tagged, separated by commas. So let us consider again the type for contact, which is defined like this. And now we can use a sum type to represent query using the three cases corresponding to the three kinds of queries. We can introduce a contact named Luke, and using that contact, it is now possible to construct a query, a value of type query, using the data constructor insert, followed by the contact, as required by the declaration of this constructor. So we get a query which is type checked, and it's exactly the same for the second query, which is now a search, which is expecting a string, so we provide a string now. And finally, you can also apply delete on a contact to construct a query for deletion. Here is another example of a sum type, and this time it is composed of constructors with no argument at all. So what we get is a definition of colors using an enumeration of the colors that are allowed as a value of type colors. So here it is possible to define, for instance, the color of Batman, which is black, and the type is inferred for this constructor to be a color. This is better than what we had when we encode a color using an integer, because now we know exactly that the only colors that are possible are black, gray, and white, and no other values. So now let's consider type T, which is defined like an enumeration using two tags, A and B. And let us assume that we have a variable x of type T. What you know is that if this variable has type T, it means that when it has been created, the programmer must have used one of the two constructors, A and B. This is a constraint, but in exchange for this constraint, you get a very strong property. The fact that an X can be either an A or a B. So you can write your computation based on that fact, which means that if you want to write some computation that depends on X, then you must provide a case for X is equal to A and a case for X is equal to B. And after that, you know that you have a computation that will be able to respond to any value, any observation of a value of type T. So what we know now is that when we observe a value of a sum type, several cases are possible. So the programmer must provide an expression for each possible case. A case will be described as usual by a pattern. And the pattern will be of the following form. You first write the tag, and after that, between parentheses, you write the patterns for the different components separated by commas. A branch is composed of a pattern and an expression separated by an arrow, just like that. And finally, if you want to represent a case analysis, you can use what is called the pattern matching, which is a very, very important construction in OCaml and which makes programming in OCaml a very, very nice experience. A pattern matching is a sequence of branches written just like that. You just write the keyword match, followed by some expression that will evaluate into a value of a sum type, and after that you write a sequence of branch. That must be at least one branch in a pattern matching. And here is how you evaluate a pattern matching in your head. Well, you just have to understand that the first thing to do is to compute the value of some expression, of the expression you want to analyze. And after that, you try to match this value with the pattern of the first branch. If it matches, then you execute the expression of that branch. Otherwise, if it does not, you try the next branch, and so on and so forth, until you find a match. Here is an example of a pattern matching. So our engine must classify the query, and given the query, call the right function. So what we do is a pattern matching over the query, and we have a branch for each possible case, one for the insertion query, and in that case, we just call the insert function, one for the deletion query, and in that case, we call the delete function, and finally, a last case for the search query, we just call the search function. Many functions in OCaml start with a case analysis over one of their arguments. So that kind of function can, of course, be written just like that. You define a function f with, for instance, an argument x, and your pattern match over x with your different branches. But in fact, this kind of functions is so common that there is a syntactic shortcut to define them. It is written just like that. You, as usual, use let to introduce your function identifier, and just after equal, you use the keyword function followed by the different branches of your case analysis. In our example of the engine function, it's just something like that. Now, what is happening in the machine? Well, each tag in the machine is represented by a small machine integer. So, when you have a value of a sum type, it is either a tag, that is an integer, if there is no argument to the constructor, if it's just like in an enumeration, or if the constructor has some arguments, then it's a heap allocated block starting with a tag. So when you do pattern matching, it's just the first thing you do is a dynamic test on this tag. And when you know what is the value of this tag, then you can choose the right branch of your pattern matching. Now, what kind of programming error you do when you manipulate algebraic data types and pattern matching? The first thing you can do is to ill-type your pattern. You can also miss some cases. But the good news is the fact that that kind of programming errors are in fact caught by the type checker. So let us define a sum type with three cases. The first one is none, and it expects no argument. Single expects one integer, and pair expects two integers. By the way, notice that the first pipe is optional, which is especially convenient when you write a type definition on one line. So, here is an invalid pattern matching because here this pattern applies none to one argument, but it expects no argument. In that case, the type checker is able to catch that error and explains that none is applied to too many arguments. Here is another example. This time, single is applied to true, which is a Boolean. But in the declaration, we can read that single is expecting an integer. So again, we'll see that the type checker is able to find that mistake and tells us that we are expecting an integer and not a Boolean. So let us come back to our type of colors in which we have only 3 colors. And imagine that we want to define a function that takes 2 colors and returns a Boolean which is true if and only if C2 is lighter than C1. To define that function, we do a pattern matching over a pair formed by these 2 colors. The first 3 cases correspond to the fact that we don't want to say that a color is lighter than itself. This case corresponds to the fact that black is darker than anything, and that white here is lighter than anything. Now, the last 2 cases corresponds to the relation between gray and white and gray and black. Do I miss some cases? I don't really know. It's a very complex example for me, at least. So I will use the type checker, and indeed I missed the cases, which is the case where the first color is white and the second color is black.